This is WK3.D. We're going to be looking at vertical circles. So we have a ball whose weight is 2 newtons, and it's attached to the end of a cord lengthwise that is 2 meters long. The ball is whirled in a vertical circle clockwise, so the ball is kind of moving in this direction. The tension in the cord at the top is 7 newtons. Tension in the ball at the bottom is 15 newtons. So the tension is more when the ball is at the bottom than it is at the top. So we have two students who are discussing the net force on the ball at the top of the circle. So we're looking at this situation right here, and we want to dissect what they're saying. We want to cross out the incorrect statements for each student's argument. All right, so at the top, let's say the tension is 7 newtons. If we look at this object, obviously we've got the tension force of the string pulling it down, but let's not forget the other force that's acting on it. We've got, the gravitational force of the Earth, which is also acting in a downward direction. So both of those forces are acting downward. Remember, strings always pull in the direction that they are directed, so the tension force is definitely pulling down. Nothing else is touching it, so there are no other forces acting on it. We just have to remember that. So we know this force is 7 newtons, and we know that the ball has a weight of 2 newtons. So both of those are directed downward. So the net force on the ball at the top position is 7 newtons, since the net force is the same as the tension. Well, obviously Dominique has forgotten about the force of the Earth, so it's pretty clear that we need to cross out his incorrect statements. Apparently everything he said is incorrect because he has forgotten the force of the Earth. 7 Newton tension force and a 2 Newton force of the Earth pointed down is not going to equal a net force of 7 newtons. Carlos, on the other hand, takes a look at it and he says, no, the net force on the ball includes the centripetal force, tension, and weight. Okay, so what is the centripetal force? Just remind ourselves, the centripetal force is essentially the net radial force that is causing the object to move essentially in that circular motion. It's not some kind of new force. It is essentially taking into account all the forces that are acting on it that we can identify from other objects. So this is not a separate force. So pretty obviously we need to say, okay, you're making a mistake by saying the centripetal force, because that's not a separate force. Tension and weight, however, do contribute to the net force. The tension and weight are acting downward. That seems reasonable, and have to be added. Okay, that seems all reasonable. Then you need to figure out the centripetal force. So he's remembering that the centripetal force has to be equal to mv squared over r to keep it moving in that circular motion. But remember, that is the net force. So this statement here is just simply incorrect. So he said a lot of things that were correct, but what he really missed out on was this idea of having forces that are only identified as things that you can point to interactions with other objects. All right, so part B. In a few short sentences, we want to essentially state the net force on the ball at the top of the circle and support your claim with evidence. So it's always good to start out with things. We're working from what's being said here, so we want to sort of use that as our starting point, and then we want to work towards with our evidence towards the point, and the point being what is the net force. So don't start there. Work towards it with evidence. So let's use some of these statements that are correct. So Carlos is correct that the net force includes the weight and the tension force. And they both pull down. They both point down so that they will be added together. Now, let's make the point. The point is we wanted to state exactly what the net force is. We've provided our evidence, and we can, therefore, the net force on the ball at the top of the circle is 7 newtons from tension plus 2 newtons from the earth for a total of 9 newtons. And then we can go ahead and we can correct Carlos's misconception if we want. We've already made our point. These two forces together add to be the centripetal force. Again, that is your net radial force. The net radial force is your centripetal force, and it's not something distinct from the other ones, the other forces that are acting on it. It is essentially the combination of those. All right, diagram right shows the circular path of the ball from part A. Remember, the ball is going in this direction around the circle. The dots represent the ball at the different places on the circular path. We want to draw free body diagrams for each of those. We're going to label the forces, and we want to make sure that their relative lengths reflect the relative magnitudes of all the forces. So let's go ahead and do point Z, because we were just talking about that. At point Z, we have, again, those two forces. We have a 2 Newton force of the earth pointed downward, and we have a significantly longer 7 Newton. We can call it the force of tension. Personally, I think I like to just label tension in strings simply as T. In this unit, that actually gets confusing a little bit because we use that same variable for period for T, so let's stick with F sub T. Now, in all these other locations, whether it be M, Q, or P, the one thing that we do know is that the force of the earth is not changing. So let's go ahead and plug in F sub E on all other ones. We want to make it the same length because the force of the earth doesn't change as it travels around the circle. But what is changing is the direction of the tensional force. The tension force, obviously at the bottom, is going to be pulling in an upward direction because that's the direction the string is located. We already know that. We were told that back here at the beginning. It's 15 newtons. So we want to go ahead and make sure that we draw something that's significantly longer than our 7 Newton one that we've already drawn. So we just want to make sure we get it nice and long to keep it consistent. At P, we're going to have the string pulling to the right. And at M, the string is going to be obviously pulling to the left. These are similar points along the trajectory, so you can guess that those two should be P and M. The tension should be the same. What about the size of it compared to F sub T at point Z? Well, it's a little bit hard to actually determine how big it is relative to the point at Z. More than likely, it's probably going to be a little bit bigger. You need a little bit more analysis In this case, we don't really have any comments about whether it's moving at a constant speed or not. We just know it's moving in a circular path. So it's a little bit hard to actually predict what those left and right f sub t's are going to be. All right, so let's go ahead and move on to part D. Here we want to derive. Derive always starts with a equation that you know probably right off of the formula sheet. So Newton's second law in this case is where we want to begin. We want to derive an expression for the minimum speed the ball can have at point Z without leaving the circular path. All right, so let's think about this for a little bit before we actually move on it. So again, as the ball is moving around this circle, we need to apply a force that keeps the acceleration the right size, so that this ball is constantly moving towards the center, is being accelerated towards the center. So the velocity is changing very specifically, and we know that for it to get there, that centripetal acceleration has to be always equal to m times the v squared over r. Now that's only for constant speed. At the top, what we have is this one point along its path where it is moving at a constant speed. At that point at the top, it's not slowing down and it's not speeding up as it is on the other side. It's slowing down as it reaches the top and then speeding up as it comes down. So at that one point, at that very top point, we can actually use our tools to analyze it with this relationship. Well, what is that centripetal force at the top that is contributing to it? We've got Earth pulling it down, we've got the tension pulling it down. So those two things together are contributing to the centripetal force that must create an acceleration. Not this m isn't there. Must create an acceleration equal to v squared over r. If it's not, if let's say the force that these generate is less than that, then what's going to happen is this ball will not be able to stay in circular motion. So it'll continue out further because it hasn't been accelerated enough towards the center because the forces are too small. If the force is larger than that, it will take a path that looks more like that because it's accelerating too much towards the circle. So we need this perfect balance between too much and too little, and that is what this provides. Well, this is the one that can't change. The force of the Earth can't change, but the tensional force will change. So that's what happens is as the string is keeping it in circular motion, the tension force is adjusting so that we get the perfect acceleration. The string keeps it in circular motion, but if we don't have enough, well, let's just go ahead and start working through this and we can see. So the sum of the forces is equal to mass times acceleration. That's Newton's second law. Since the ball is in circular motion, the acceleration is the centripetal acceleration. So at that one point, we have that force diagram where we have the downward force of the Earth and we have the force of tension as well. So we can go ahead and on the left side of the equation, we can plug in the forces. So let's go ahead and just call down as the positive direction, or that's actually our radial direction, our centripetal direction. So the force of tension plus the force of the Earth has to be equal to m times the centripetal acceleration. So we have to describe what we're doing. I'll just describe it verbally, but you would want to write this. We could say something like the two forces on the ball at the top of the circle are the force of tension and the gravitational force, both of which are exerted downward or towards the center of the circle. So we've given them a positive direction. So then we would say, maybe the next one, we want to go ahead and we want to plug in what that acceleration has to be equal to. So here we would say the centripetal acceleration can be represented by velocity squared over radius. So every step along the way, so the first thing we did was we plug in forces, and now this is our knowns. This is a known step. We want to be a little more specific than that. So what's happening at the minimum speed? So there is some minimum speed. So the speed, let's look at this relationship. As the velocity gets smaller, as it goes slower and slower, this side of the equation has to get smaller as well. Mislabeled that. Well, which one of these can get smaller? This one obviously can't get smaller. That's the force of the earth. But the tension force can get smaller. So the amount that the string is pulling gets less and less and less. At some point, though, the velocity is getting so slow that this can't get any smaller. The smallest it can get is 0. So what we're left with is this place where we've reached the minimum velocity. So how would we represent this? We would just say that the force of the earth is equal to mv squared over r. So we could say something like ft equals 0 at the min velocity. And then we have a step where we plug in our knowns again. We know that the force of the earth is equal to mg. That's again plugging in knowns. And then we would want to solve for our velocity. And again, this is the minimum velocity that we can tolerate. So again, what would happen if the velocity is lower than that? Well, at the top of the circle, we would no longer follow a circular path, but we would start to follow a parabolic motion, because the string essentially would not be pulling anymore, and we would be in just what we call projectile motion. Suppose the string breaks at point P. Describe the motion of the ball after the string breaks. When we describe the motion of the object, we want to discuss what's happening with position, velocity, and acceleration. Tell the story of the motion of the ball from the time the string breaks until the ball reaches the ground. So at point P, what's happening right at point P? Well, we've got the ball coming around here, and suddenly it hits this point. So at that point, all we need to know about its motion in the future is to know what is happening with the forces exerted on it and its initial velocity and position at that point. So at that point P, if the string breaks, what is the force diagram on it? Well, there's only one force acting on it. It's the force of the earth, because the tension here broke. The string broke, so we just have the force of the earth exerted on it. At that point, the velocity is initially going up. It's moving. The velocity is tangential to its circular path at that point. So the velocity is going to be going up, and we can pretty quickly describe what's going to happen. We know it's in just essentially free fall motion, but it's going straight up. So it's going to go up, up, up until it stops, and then it's going to come back out all the way back to the earth. So we could say something here like the ball travels straight up to a max height and comes straight back down. Velocity-wise, we would say something like the speed of the ball decreases until it reaches the maximum height, at which point the ball turns around and speeds up until it hits the ground. Acceleration-wise, the acceleration of the ball is always 9.8 meters per second down after the string is cut. So you could even kind of, if you wanted to kind of sketch that out to help yourself understand what that would look like. We're just kind of looking at this y dimension, so we go up, up, up until we reach that height, and we come back down. That shape is going to have a parabolic shape because a curved shape. The velocity, on the other hand, is going to start out moving in the positive direction, got a positive slope, and then it reaches zero slope. So it reaches the peak height, so zero velocity, and then it has a negative slope. So it would go something like this. It's constant acceleration motion. This point here would correspond to that point there. And then acceleration-wise, it's always negative 9.8. Doesn't change. All right, that's it.